Good afternoon and welcome to Wavelogix Break Free Lunch and Learns. My name's Suzanne Florek and I'll be your host today. Our guest is Joe Turek, President and COO of Wavelogix. Joe Turek received his bachelor's degree in electrical engineering in 1979 from the University of Notre Dame and an MBA from Northwestern's Kellogg School of Management in 1982. He's been involved in manufacturing his entire career. He holds 5 patents involving high-performance microwave telecommunications, circuit board technologies, and has been registered as a professional engineer and member of the IPC and IEE. These webinars are produced and brought to you by Wavelogix. Wavelogix emerged in 2021 from a partnership between the Indiana Department of Transportation and Dr. Luna Liu's team at Purdue University, aiming to reduce road and bridge failures while minimizing traffic disruptions. Our breakthrough technology, the Rebel Concrete Strength Sensing System, offers real-time, in-place measurements of concrete's elastic properties, providing a more accurate and efficient alternative to traditional maturity sensors. It's versatile, it supports highways, bridges, commercial, and precast projects, and enables construction teams to make faster, data-driven decisions. Wavelogix patented technology eliminates the need for pre-established maturity curves, ensuring easy-to-use, accurate results for any concrete mix, optimizing schedules, and reducing costs for construction projects. So with that all being said, I'm going to let Joe go on and tell us all about it.
Thank you, Suzanne. Okay, guys, let's get started. This is kind of exciting. Concrete is the #1 building material in the world, and yet it gets a very bad rap when it comes to CO2 production. And we're going to talk today about how our Rebel sensor can help contribute to going greener with concrete. But first, let's talk a little bit about concrete, kind of understand that. What do we actually produce annually in terms of concrete? Concrete in the United States is somewhere between 500 and 750 million tons of concrete are produced in the US alone. Worldwide, it's like 20 billion tons of concrete. If you look at the producers and users of concrete today, China, no surprise there, is the largest user of it. Almost half that demand, 10 billion tons of concrete are poured annually in China alone. India is ranked second, and they're only 1/5 as large as China with 2 billion tons poured. And then the US ranked fourth is only 1/4 as large as India, somewhere between 500 and 750 million tons of it. The rest of the world represents 1/3 of that usage of concrete at around 7.5 billion tons. So a lot of concrete being used around the world. Again, reason for it being the #1 construction material. Why? Because it's easy to produce anywhere in the planet. We have the raw materials that we need. If you look at concrete, it's basically cement, it's large aggregate, gravel, small aggregate, which is sand, and then water. And you've got yourself concrete, and a great building material that's been used since the times of the Romans, if you believe that. If you look at the production of cement, again, it's going to fall right along with the usage. Cement is only about 1/7 of the amount of overall of the concrete. And China, again, is the leader of that. India, second, Vietnam, and then a whole host of other countries, United States, the Middle East, Brazil, the Far East, Russia, Egypt, South Korea, all kind of fall in line there. So big producers of cement. Now, when we talk about cement, not a lot of people, we always talk about concrete, but not everybody knows how cement is made. So the reason why it gets a bad rap with a high carbon footprint is if we just look at how it's produced. Cement is quarried, limestone quarry, then it's trucked over to a crushing machine. It gets crushed and then put into a finer powder. And then we mix in things like clay and sand to be able to create a chemical reaction. We grind it again, mix that all up. We start to heat it, and then we fire it in a kiln at 1450 degrees centigrade. And that we take that stone and we drive out all the moisture and water out of it and create a new stone combination of that sand, clay, and limestone into a clinker. So we create another stone, and then that clinker is cooled. We mix in some fresh gypsum with it. We grind it up, turn it into a powder, and then we put it in bags or shipping containers, and off it goes to the end customer. So kind of fascinating way to make the cement that we use today. And the nice thing about cement is that it can actually be ported economically around the world. If we look at the overall use of cement in the carbon footprint of everything in the world, it represents 8% of the entire carbon footprint. And although it's the smallest portion of what's being produced in the world, it still is incredibly significant. Not only that, when you take cement now that we've cooked at 1450 degrees centigrade, and then we add water to it, it's an exothermic reaction. So now it's releasing even more heat in the operation. And usually when you pour concrete, that temperature can get up to, oh gosh, around 70 degrees centigrade. So it's a big producer of heat. It uses heat to create itself in that. And because of that, every pound of cement releases about 0.93 pounds of CO2, almost a 1-for-1 in cement. And again, as I said, cement accounts for approximately 1/7 of the total weight of concrete. So why is that important, and what happens in concrete? So when we pour concrete, concrete is great, but what we need to do to do our next operations is we need to understand what the strength of that concrete is. Concrete, when it cures, it's going to cure somewhere around 3,000 to 5,000 to really high concrete strength might be 10,000 PSI. But there's a lot of operations that we do early on, within the first couple of days. It gets to a certain amount of strength that allows us to do things like remove our scaffolding, remove the forms, post-tension the concrete, cut it, and do our next operations, release traffic if you're building a road. Those all happen in the first couple of days. Final strength takes about a month for concrete to cure to about 97 to 98% of its total strength. So it's a long time to cure, but early curing is really important for us to do in the next operations. So how do we know what that strength is? Well, the 100-year-old technology has been to use a companion cylinder or companion beam. And then we take those cylinders in a periodic interval, 1 day, 3 days, 7 days, 14 days, 28 days. We crush those cylinders and we determine what that strength is at that particular time. And unfortunately, it's not real time. It's time consuming to make these cylinders. It typically requires skilled technicians, which are getting harder and harder to find. And there's large potential for error. If I show you this slide, this is really kind of fascinating. We talk about the error in the cylinder process, which has been what we've been using for the last 100 years to determine strength. If I look at this red line of a particular mix, a study was done in California a couple years ago. It was kind of fascinating. They took a known concrete mixture and a known curve of how it grew in strength over time. So you can see from 10 hours to 20 hours, in terms of days of how it aged. And if you look at the compressive strength of that aging concrete, they had over 200 trained technicians make cylinders, crush them on a periodic basis, and then report their findings. And these dots represent what they found at that particular time interval. And you can see it's all over the map. There's almost 400 to 500% variation from what a true strength was to what the technicians were reporting. And that's a problem in our industry today that we've experienced, is that our technology to determine the strength has been inferior to its actual true strength. We'll keep that in mind. If you look at the impact of those cylinders that we're doing and using for testing purposes, we produce about 15 cylinders for every 100 cubic yards of concrete. Those 15 cylinders, then, it's usually 3 cylinders are broken at 1, 3, 7, 14, and 28-day intervals. They represent about 150 pounds of concrete per test. That's huge. If you do the math on that, that's the 750 million tons of concrete in the USA alone, used alone, okay? Turns out to be about 40,000 tons of cement if we convert that over to cement in that concrete. And those 40,000 tons of cement translate to about 38,000 tons of CO2 produced annually. And if you look at it on a worldwide basis, that's 1 million tons of CO2 that we're producing just by using cylinders for testing. And then we throw those out. So not only are we're overproducing in CO2 with cylinder testing, but then we've created that much more in waste that has to be landfilled or disposed of. But that's not the whole picture. So cylinder testing is one of the first problems with CO2 generation in concrete. But the second one is because the dirty little secret is contractors are paid for final strength. And if they don't meet the final strength of their specification, so a concrete mix might be specified at 5,000 PSI. And so typically at either 28 days, and today it's getting even tougher, maybe 56 days, the contractor has to hit that strength or higher that they were contracted to do in 28 days. Now, if you see in the previous slides where we might have a 400 or 500% error in actually getting to that strength, what does the contractor do to guarantee that they're going to get paid? Well, human nature is we end up adding about 20% more cement to that concrete mixture than is needed to guarantee that we get to that strength and get paid. Because if you don't get to that strength, a couple things can happen. You get paid less, you don't get paid at all, or you might be required to remove the concrete structure that you put in place and replace it to get there. So hitting strength is really important. And if you look at that 20% of excess cement in there, we're going to be producing an extra 500 million tons of CO2 annually. And that's a big number because of that. So what are the other things that the industry is trying to do to reduce the carbon footprint of cement? They're looking at replacements for cement. Let's substitute some of that cement. So if you don't have to use all the cement, let's try and replace any percentage of it. And right now we're targeting about 25% replacement of cement. We have been using some replacement forms called SCMs, supplemental cementitious materials, and those have been byproducts of some of our industrial processes, like slag production that comes out of the steel industry, like fly ash that comes out of the coal production in energy production. And so those are some of the SCMs that have been used classically, but those processes are going away in the United States. So now we're looking at all sorts of other types of things that can be cutting down the use of cement and replacements in it. And as we're doing this in an industry, we're adding some more limestone, for instance. We're adding other SCMs, and we're coming up with new materials. But every one of those new materials has to be defined, tested. We need to make new mixes. And when you make new mixes, you need to create more cylinder breaks to be able to determine the strength. But if we can reduce the amount of cement used in concrete for every ton cuts almost another ton of CO2. So this is where the Rebel system comes into play, which is what's really kind of exciting about our technology, because one of the first things we're trying to do is we've got a IoT type of sensor, and this sensor is embedded in concrete. It's plugged into a data logger, and the data logger takes the information, the data it collects from that sensor, and then sends it to the cloud. But our technology is working towards eliminating the need for using cylinder breaks, because we're giving real-time concrete strength as the concrete cures. And that's what's so cool about our technology, really. It's accurate, it's reducing human error. You don't need trained technicians to be able to produce the information. And it's a great way to quickly evaluate some of these new low carbon alternatives in their mix designs, because you can come up with a new mix, you can throw our sensor in there, and we can be giving you real-time data on how that concrete strength is growing over time in real time. That's really, really powerful. So how does our system work? As I kind of mentioned, you take the sensor and you embed it in your structure. The data logger is not embedded in the structure. It stays outside that structure. It is reusable. The sensor is a one-time use. That data uses the cellular infrastructure, LTE, and sends that information into our database in the cloud. We have a machine learning algorithm that works on that data and converts it into strength. That strength is shown on a user interface that you can see right on your phone or on your laptop or tablet, anywhere on the planet that has internet connection. The strength is just what we're used to seeing. It's a real-time curve that tells you the time in days against the strength that's being generated in a nice little curve. It happens over real time. And we also add temperature probes both in our data logger and in the sensor, so we can show you the temperature of the structure in real time, along with the ambient temperature of outside the structure. And those things are also very, very powerful for use in the contractor world when you're building a structure, knowing both a combination of what the heat is and what the strength is. How does our product work, and why is it different than cylinder breaks? Well, we're using piezoelectric sensors to actually create a wave that pushes itself into the concrete as it's curing. And that way we're measuring the impedance or the resistance or the pressure that wave is pushing against the cement. And the really interesting thing is that when you look at pressure, and here's a representation of what that wave pressure looks like as the frequency is changing, that when you get to the resonant frequency of the structure, you will see the wave itself grow. So there's a lot of back pressure here on the wave. You can see the wave, it's getting this pressure. And when it hits that sweet spot or the resonant frequency, boom, now you get all this energy. You have no resistance or very little resistance, and you see that wave grow. If we plot that and we look at where the least resistance is for that wave, we can see a defined peak in that frequency. And we run the frequency from 20 hertz to 200,000 hertz. You're going to find that peak. Now, what's so interesting about that peak? Well, for number one, we found that peak non-destructively. We didn't have to crush a cylinder. We see that peak. But that resonant frequency of that structure is proportional to the modulus of the structure, and the modulus is proportional to the compressive strength. So by knowing this point of the resonant frequency, or this frequency, we can determine the compressive strength in real time without a destructive process. Now, the cool thing is you say, well, that works great with a structure that's solid, but what happens when concrete is curing? Well, sure enough, if we embed it in concrete, as soon as there's a modulus, as soon as the concrete starts to harden enough to have some pressure, some strength, we can start to see that resonant frequency, as it cures, then changes and moves along And these represent different PSIs, 120 PSI, 500, 1100, 2000. And we can see that that resonant frequency changes, the modulus changes as the concrete cures. And that's exactly what we would expect. And that is the basis and the thrust of our technology today, and why we can do real-time strength more accurate than any other company's product on the market today. It doesn't need to be calibrated. It's agnostic to any type of concrete mix design, and it gives us accurate results. So let's add this all up when we look at the carbon impact, what we're doing today. What are the improvements and things that we can actually affect concrete today to help reduce the carbon footprint? Well, cement produced, again, as we talked about, cement in the USA, about 100 million tons, worldwide 2.7 billion tons. That impact is about 2.5 billion tons of CO2. Cylinder brakes represent a small portion of it, but still significant. About 1 million tons of CO2 could be reduced in the world if we eliminated cylinder brakes completely. If we look at over cementing, the process that's being done to guarantee the contractors get paid, if we can give them real data that shows them they can reduce that right off the bat, we can save about 500 million tons of CO2 just by reducing that excess cement. And if we come up with just 25% cement replacement with other alternatives to cement, we can reduce the carbon impact again by 22%, little over again 567 million tons worldwide. Overall, right now, we have in our grasp, we believe, the ability to reduce about over 40% of the carbon impact in a very short period of time, probably by the end of this decade. So that's where we are today, using our technology to help us reduce our carbon footprint using the Rebel sensor. We're doing our part to help reduce over cementing, analyzing new carbon mixes, and eliminating cylinder brakes. And so for more information, please feel free to scan the QR code. And we have a great offer going on right now where we're giving you 2 free Rebel sensors to try on us to check out our technology. So right now, I'd be happy to take any questions that you have and answer those. Suzanne, I'll turn it back over to you.
Well, thanks, Joe. That was a great discussion. And I do have several questions here. One of the questions that we have is, what is the current global carbon initiative for CO2 reduction?
I think that's a great question. Well, as I mentioned right now, there's actually the initiative by the end of this decade, 2030, to reduce the carbon footprint by 40%. And the government of the United States right now is dedicated to doing that. I think that's well in our grasp. The overall goal is by 2050, 20 more years later, to have carbon zero, so a carbon neutral impact of concrete. And that's going to end up being probably activated by having replacements for cement, either completely or with additives that might be negative carbon footprint, that when you add that with the positive carbon footprint of cement, will end up being carbon neutral. And from some of the things that I've seen already being presented, I think we're going to get there.
Well, Joe, that is a lofty goal and one that I think we can achieve with our whole society globally. And I know you did point out during the webinar a lot about how Wavelogix technology really can impact that carbon reduction. But would you mind just going through that one more time so we're all clear on why your technology really helps?
So the number one way that we can help is reducing or eliminating the use of cylinder brakes and flexible beam brakes. So if we can save the carbon impact right off the bat by eliminating those cylinders. We think it's an old technology. We think it's inefficient. We don't think it's very accurate. And we have a device that is less expensive, real-time accuracy, and easy to use. So that's the most significant. The other ways are we can help contractors over time help reduce their material over cementing the material, which over cementing today is as much as 20%, and then help the industry continue to analyze new mix designs very rapidly. And it's that rapid analysis that allows us to get new technologies out into the market quicker.
This next question I think you just answered, which was, will reducing cement mix design hurt the performance of concrete strength? Maybe you just want to talk about strength a little bit more there.
Yeah, that's always the concern. I mean, what gives concrete its strength is the glue that holds all the aggregates together, right? And we know that if you add more cement, you're going to get a stronger material, which is why contractors sometimes over cement to make sure that they hit that range. The biggest fear is that when you start putting other additives or substituting cement with something else, you may not get the strength that you really are expecting. And if you can't get the strength, then we failed in a substitute. So there's a lot of work going on to guarantee that you get the strength. And that's one of the reasons why it's nice to have a tool that can analyze the strength of concrete. And the other thing that's important is the strength over time curve. So if you see concrete growing over time, it can grow very fast. It could grow very rapidly in the first couple of days and then level off over a long period of time, or it can go very slowly, a slow rise over time. And those things are kind of important in terms of the characteristics of how we build things today. And so some of the replacements may or may not work as well. And you want to know what that looks like, what that curve looks like in real time. And again, that's how our Rebel sensor system will help the industry use a tool that's gives them good data in real time.
Great, thanks, Joe. One more question is about, does Wavelogix technology work with alternative cement mixes that are replaced with low carbon alternatives? I know you touched on this briefly, but maybe you want to talk about how important the mix design is to be shared with Wavelogix in these situations, and what happens when people do that.
There are some other technologies that try to measure concrete strength in real time, but they need to be calibrated to each mix design. And so that makes it very clunky. It also requires you in the calibration process to use cylinders as a guide to actually do that calibration. So it's somewhat anti-productive using that technology. It's also only used for and only good for about 1 or 2 days. It can't go the distance. Our sensors could be used for the life of the structure if you wanted to, but certainly can go 28 or 56 days to give you strength. You can come back a year later, you can measure the strength again. You can do that indefinitely. So that's one of the things that differentiates us. But as I just mentioned, because we are measuring using the piezo technology with wave propagation into, or the pressure of a wave going into the material, it's agnostic to a mix design. So it doesn't matter what you use in terms of your mix. So if you're substituting other types of cement or other types of materials, we're going to tell you the true strength of that new mix design, which again makes our tool the most powerful on the marketplace to give you real-time strength. And you may come up with a mix that isn't a good design for concrete. It might have a poor strength. We're going to tell you that. We're going to show you that it may not be good. We're going to show you it's really great. We're going to show you how it works because of the way that we use our technology.
Great, Joe. Thanks for explaining that. I have 2 more questions that have to do with the Rebel system itself. And one, is it available to purchase today in production quantities? And what's the cost of the sensor and Datalogger?
Oh, those are really good. The product is in production now. It's being deployed out across the country. We have it being used in over 20 states right now with the federal highway DOTs. We have it being used in vertical applications, in slab work, in tilt-up, in precast, anywhere where concrete is being poured. Our sensor works in those applications. And we have stock. We can ship within 24 hours, virtually any quantity that someone needs. We have the starter kits that are used for testing and analysis, trials. We're ready to ship. So within 24 hours, we can ship you the product that you need. Just have to talk to the sales department. They get them going there. The product in single quantities, the sensors run $399 each, and the data loggers, which are reusable, run $14.99 each. And in volumes and in special offers and kits that we have, those prices come down. We've got some really great special offers right now for introducing the product. And talk to our sales department, and they'll be happy to get your quote immediately.
Well, I just would like to thank you as the host of this show today for joining us and teaching us all about the Carbon Initiative and CO2 reduction. Your time was fabulous, and we would like to let everyone know that you'll be back again on October 31st, speaking about cutting costs and how the Rebel system sensors save labor in construction projects. So please come back and register for our next Break Free Lunch and Learns with Joe Turek.
Great. Thanks, Suzanne. Appreciate it. See you, everybody. See you next time.